Hello everyone, my name is Putu Krsna and today we are going to be discussing about Hooke's law. Hooke's law is a law of elasticity discovered by the English scientist Robert Hooke in 1660. It states that for relatively small deformations of an object, the displacement or size of the deformation is directly proportional to the deforming force or load. Under these conditions, the object returns to its original shape and size upon removal of the load. Elastic behavior of solids according to Hooke's law can be explained by the fact that small displacements of their constituent molecules, atoms, or ions from one position is also proportional to the force that causes the displacement. Now, we're going to talk about Hooke's law equation. First, we are going to find how we are going to find the force in Hooke's law. We can use the usual equation, which is mass times gravity, or you can use the force constant times delta L, which is the difference between the stretch spring and the not stretch spring. Secondly, we can search delta L with 1 per force constant, which is K times force. Now, third one is how to search L1, or what is the length of the spring after it's been stretched, which is LO, that is what the length of the spring is before it's stretched, plus mg, which is m times g, mass times gravity per k, which is force constant. Now the fourth one is how we are going to search the force per area in the Hooke's law. First, we're going to use E, which is the modulus elasticity or modulus Young of the material, times delta L, which is the difference between stretch spring and not stretch spring, per LO, which is the length of the not stretch spring. Now, we're going to tell you about the tools that we use for Hooke's law experiment. First, we use climb and stand to hold the ruler up. Second, we use the meter scale with 1 meter scale that is in millimeters, which means it's 1000 millimeters. We use 2 springs and silk thread. The 2 springs, the first spring has 0.5 meter in diameter and 0.3 meter in diameter. Third, we have slotted weight. Fourth, we have weight holder. Now, we're going to tell you about how we do the procedure. First, we have to set up the experiment. Then, we hang the weight holder and measure the length of the 2 springs and silk thread. We then add the slotted weight still and take note of the weight and pointer position. Repeat step 3 until the weight reaches 180 grams. Then we repeat step 1 to 4 on the different springs and silk threads. Now, this is our first spring data collection, which the XO has the length of 16.5 centimeters. Now, you can see that the weight, 20 grams, 40 grams, 60 grams, it gets heavier until it's the last 180 grams, which with every gram that it's slotted with, it gets more stretch and the length gets higher. You can see it by the delta L. First one with the 20 gram is 10 centimeters or 0.1 meters. Now on the 180 grams on the other hand, you can see the delta L is 58.2 centimeters or 0.582 meters. Now, the below one is force. We search it with mass, which is 20 grams. With example, 20 grams converted into kilograms, which is 0.002 times 10, which is the gravity. Mass times gravity equals 0.02. Secondly, we can use the data collection on second spring. On the second spring, we get the length of the spring is 19.8 centimeters. But because it is more short than the first spring, the delta L is shorter, which you can see from the 20 grams. Only getting the delta L is 0.7 centimeters, and the 180 is 8.9 centimeters, which is really a far cry from the first spring. Now, the force is the constant across the board because it uses the same weight. Now, we're going to talk about the last one, which is the data collection of the silk thread. Now we can see that this silk thread have a length of 21 centimeters. The delta L is the second highest behind this first spring, which is 1.5 centimeters on the 20 grams, but on 180 grams is 11.5 centimeters on delta L. Here we see the first graph. We see the graph of the first spring, which is, you can see that. Second spring graph, you can see that the numbers are smaller than the others. And the third one, you can see that, it's second in place on the scale of delta L. Now, lastly, we are going to search to find the force content of each of the spring of the experiment we did. Now, the force content, we can find force content with 1 times F weight, which is force, 1 times force per delta L. Now, you can use anything with the force, but I'm going to pick the most highest one, which is 0.18 Newton from the 180 grams weight per 0.582 meters equals 0.309. And the second spring. The second spring we can use as like this first spring is 0.18 per 0.089, which we find 2.0222 on its force constant. And on the silk thread is 0.18 per 0.115 which equals to 1.565. Now, as you can see here, we can see that first spring, even though they have the most delta L, is the most small one, because while the second spring, which have the shorter delta L, has the larger one. This is because we can see that the stretching force increased the extension of the spring also increases. This agrees with our prediction. In fact, since the line of the best fit is a straight line through the origin up to a certain point, we can be even more precise. We can say that the stretching force F is directly proportional to the extension E up to a limit known as the limit of proportionality. Thank you for listening.